Searching. Alright, searching techniques now we can look at in this section. We know we have that linear search give you big of n, binary search give you log n. Now we're going to look at a technique that called hashing, give you big of 1 when you search by values. Linear search is when you don't care about order. When you insert something into the list, right, last slot for array, first slot for linked list. And when you search the list with a given key, it's going to compare from the beginning of the first element into the list. And we search for the elements by examining each subsequent element's key until either the search is successful or we never found it on the list. Because on the number of comparisons is cost you O(n) for linear. The worst case, we have to make n key comparisons. On average, assuming that there's an equal probability of searching for any element in the list, we make it n half, like divide by 2 comparison for a successful search. So that's an average. High probability ordering. Sometimes a certain list elements are in much greater demand than others. We can then improve the search. Put the most often desired elements at the beginning of the list. So this we just do high probability ordering. So using this scheme, we are more likely to make a hit in the first few tries, and rarely do we have to search the whole list. If the elements in the list are not static, or if we cannot predict their relative demand, we can move each element accessed to the front of the list. As an element is found, it's swapped with the element that preceded. So this is a technique that we use in the operating system. Or like Word document, you have the recently open document, you can just go to open it again. So this is a technique that they use, high probability ordering. Since we open that document, it's most likely that we're going to open it again. Or the technique that you use in hardware design, when you do hits for, when you search, you have to put things from hard disk to RAM. So we like to put those data that we recently used into the RAM and the cache memory, so that we don't have to go to the virtual memory on your hard disk, which costs longer to access. Lists in which the relative position of the elements are changed in an attempt to improve search efficiency are called self-organizing or self-adjusting lists. Sorted lists. If the list is sorted, a sequential search no longer needs to search the whole list to discover that an element does not exist. It only needs to search until it has past element's logical place in the list, that is, until an element with a larger key value is encountered. Another advantage of linear searching is its simplicity. It's very simple, right? The binary search is usually faster, however, it's not guaranteed to be faster for searching very small lists. As the number of elements increases, the disparity between the linear search and the binary search grows very quickly. The binary search is appropriate only for list elements stored in a sequential array-based representation. However, the binary search tree allows us to perform a binary search on a linked data representation. Hashing. So hashing is relying on the hashing function as a technique when you search. Like for example, I'm looking for an employee from employee list. So employee has index 00 to 99, so we have an array which has limit size 100, right? But employee ID is 50,004. Now, if I look at this employee and I want to find this employee right away, in linear search, we have to use a big array, right, to store this 50,000, maybe array size of 60,000. And then we have to do one by one. If it's sorted list, it's going to cost you 50,704 to find that person. We said, why don't we just create a hashing function instead and make a temp array? Like, this is like a temp array that we're talking about, like recently search, like recently used, we put into this array. And this is smaller size of array, 100. Whenever we need this ID, we just put it into hashing function, which is mod by, take the ID mod by 100. Now you get the index as 4, right? Index 4, you map to a 4. So this person should store in that location, or data of this person can be found or accessed in that location right away. Because this is just employee list like temp that holding all the employee list ending with 04. So that's the technique of hashing. So hash functions, you may see that the original list itself could store in the hard disk or on the database. And we only look at the interested employee and put in the array list, which is smaller size with hash function. So hash function, a function used to manipulate the key of an element in the list to identify its location in the list. Hashing, the techniques for ordering and accessing elements in a list in a relatively constant amount of time by manipulating the key to identify its location in the list. Hash table term used to describe the data structure used to store and retrieve elements using hashing. So we want to look at an example when we implement hashable interface here. So we require to have one method called hash. So it's a mathematical function used to manipulate the key of an element in a list to identify its location in the list. That's the hash or hash function. So let's see. We start to have, since this is the data structure, we have the method for add and get. So we're going to add, when we add the elements into the hash table. We have to rely on the hashing function, right? So we create location variables and try to pass into, call the hash. Then we get the location that this element should go. And then we insert in that location and increment the list. And when we get, we just pass the elements in and call the same hash function. It's going to, because the element itself has its own hash function, then it's going to return the same location back and we hash back. You may see this only costs 1 to add and costs 1 to get for big O. Now when we do this hashing, like we said, it's smaller than the original list. So it could create a collision, like it could be having two employees that ending with the 04, right, ID. So this is called collision. The condition resulting when two or more keys produce the same hash location, like employee with 50,704 and 50,804 is going to return the same index 4. So this is called collision. So how to resolve this hash collision? One technique we use linear probing. By sequentially search a hash table beginning at the location returned by the hash function and search for the next one. So we revise the add here if we want to linear search, right? So we say while list location not equal to null, right? After you hash, you get location, and we check at that location. So it's not equal to null. That means there's collision, right? So if not, then we just put it there. But if there's collision, we just say location plus 1. Just go to the next one. Right. Now we have to mod with the list.length because in case it add the index 99. So if it add the index 99, if it's at index 99, it's going to do mod.list.length. It's go back to index 0. So it's just linear probe into the beginning again. And it's keep doing that until it find the location is null and put that into it. So that means we have to revise the get to do the same implementation to get the location back. Do linear probe. So this is that example. Like if somebody employee ID 50,003 is already in location 3 and 104 in location 4. And we try to insert 77,003 add into the elements. So you see we mod 100, we're going to have collision with 50,003. So linear probe is going to find the next slot. It's not vacant, it's not null, then it's next slot. So now we found that we have to put 77,003 into location 5. So that's the technique. So an approach could be removing elements. So if we want to remove an element, so this look at how to remove now. So if we want to remove a approach is same, call remove method pass elements, set the location to element.hash, and then just go to the location and put it to null. But if there is a collision, we have to use the same linear probe. Collision complicates the matter. We cannot be sure that our element is in location element.hash. We know that. So we must examine every array element starting with location element.hash until we find a matching element. We cannot stop looking when we reach an empty location because that location may represent an element that was previously removed. There you go. So that's going to complicate the issue now if we have the remove coming in. So this problem illustrates that hash table in the form that we have studied thus far are not the most efficient data structure for implementing lists whose elements may be deleted. Right? If you delete it, it's going to cause other issue now. How we going to know that the next location that we find to remove is actually the elements still there or not? So we have what we call clustering technique. So the tendency of elements to become unevenly distributed in the hash table with many elements clustering around a single hash location. Right. So this is what is going to occur to, right? Rehashing. Resolving a collision by computing a new hash location from a hash function that manipulates the original location rather than the element's key. Quadratic probing. So resolving a hash collision by using the rehashing formula. Right, with a square here, mod with array size, hash value plus or minus I square. Random probing, resolving a hash collision by generating pseudo-random hash value in successive application of the rehash function. So these are the other techniques besides linear probing. We can do quadratic probing using the quadratic formula, or just random probing using the random values for the hashing location. We have buckets and chaining. Bucket is a collection of elements associated with a particular hash location. So we create a bucket and push into a bucket, like a stack, push into a stack, instead of do linear probing. Chain, a linked list of elements that share the same hash location. So look at this, 7703. We have 50,003. We can